Okay, good morning, students. Today we are going to talk about the three representations of numbers: sign and magnitude, ones complement, and twos complement. These are the three representations what we use for the number representation. So sign and magnitude, say for example, I want to represent the numbers from 0 to 3. 0, 1, 2, 3. So it is 0, 0, 0, 1, 1, 0, 1, 1. I am talking about the sign and magnitude initially. Okay. Then ones complement, then twos complement we'll talk about. So this is 0, 1, 2, 3. But sign and magnitude, what do you mean by sign? You should add a sign. So if it is positive, that is plus 0, plus 1, plus 2, plus 3. So plus means the sign is 0. Okay. So for the negative numbers, that is for minus this one, we represent them with a sign of 1. So if I want to represent minus 3 and 1, then 2, minus 2, I will represent 2 and this is minus. For minus 1, 1 is 0, 1 and sign is 1. For 0, it is 0. For minus, it is 1. So this is how we represent the numbers. Okay. So now, whenever we are talking about this, can you see something vague in this technique? That one thing what we can see is two representations for 0 here, plus 0 and minus 0, which is not true at all, right? So be it your ones complement, twos complement, or sign and magnitude, for positive numbers it will be the same. Okay, it will be the same. For negative numbers, in ones complement, it will be different. So this will be 1 0 0. Okay, so this will be your minus 3. This will be 1 0 1 1 1 0 1 1 1. So here also you have two representations for your 0, which is again not acceptable or not true. Then we go for the twos complement method. In twos complement method, for positive numbers it is the same. For negative numbers, it will be different. So here whatever we are seeing here for ones complement, you'll add 1, you will get twos complement. Okay, so I have just taken for numbers from 0 to 3. You can also check out this representation here, whatever I showed you just now. This is the representation for sign and magnitude. Just now whatever I showed you. This is for ones complement, where you have two representations for 0 even in ones complement. In twos complement, what we do, you will be adding 1 to the ones complement to get twos complement. So this is the representation for the twos complement. But if you check here, you don't have two representations for 0. It is a single representation for 0. So that is why your twos complement method is widely used in your systems for representing, because here you have two representations for 0, here also you have two representations for 0. So these two methods are not used. They make use of twos complement method. Okay, so this is where we use twos complement for subtraction. Okay, and you will see even in your multiplication and all, we will be making use of this twos complement method. So if you just see here, this is for numbers from 0 to 7. For positive numbers 0, 1, 2, 3, 4, 5, 6, 7, what you all can see here. Okay, so the first one what you can see here is 0 to 7 for positive number, whether it is sign and magnitude, whether it is ones complement or twos complement, it is the same. For negative numbers, it is different. Okay, so if you have to represent 8, 9, 10 up to 15, so if you negate those numbers, what is it? Minus 8. This will be minus 7. How do you know it is minus 7? If you convert this back, 0, 1, 1, 1. So this will become plus 7, means this is minus 7. So how do you know this is minus 6? So 0, 1, 0, 1 and add 1 to this, 0, 1, 1, 0. So this is plus 6. Correct? So means this is minus 6. Like this, these are the representations. Okay. Now, quickly I will take you through the addition and subtraction of numbers. So how can you perform the addition and subtraction of numbers? Say for example, they have given you to add 15 and 10, you think. Okay, how do you represent 15? 1, 1, 1, 1. And 10 is represented as 1, 0, 1, 0. I think by now you all are aware of this. 2 power 0, 2 power 1. This is 2 power 2. This is 2 power 3. Correct? So with that I've got this values. Now you add 1 plus 1. 1 plus 0 is 1. 1 plus 1 is 0. Carry 1. 1 plus 1 is 0. Carry 1. 1, 1, 1. See, 1, 1, 1 is 3. So how do you write 3? 1, 1. So add the rightmost bit 1, then carry this. So you'll get 1, 1, 0, 0, 0, 1. This we call it as the overflow, because with 4-bit number you can represent maximum up to 15. If it exceeds beyond that, it will go to the next bit. So it was 25. So see whether our answer is correct. This is 2 power 5 means, I'm sorry, 2 power 4 means 16 plus 9. 16 plus 9 is 25. Our answer is correct. Okay. Addition is easy, no problem. But when you are doing subtraction, say for example, I want to subtract something like this. Okay, I want to perform the subtraction. How do you perform the subtraction? Normal subtraction. 1 minus 0 is 1. 0 minus 1 I cannot subtract because 1 is greater than 0. So I have to borrow. So if I go to borrow for the next digit, it is also 0. So this will borrow from this. So this will become 0, and this has borrowed 1. So you should put, you have to mind here that you have to put 1 to the left. So it becomes 2. Okay. Now I have to borrow from here, right? So when I borrow 1 from here, this becomes 1. Out of 2, 1 I borrowed. So here I'll put 2. 2 minus 1 is 1, and 1 minus 1 is 0. 0 minus 0 is 0. So I had taken 9, 1 0 0 1. 9 minus 6 is 3. Can you see? You got 3. But this is, see, what I'm showing you is just for 4 bits. But in practice, you'll not have like that. You'll have huge number of bits. So this will take a very, very long time for performing. So they make use of 2's complement method for performing this subtraction. So what we will do is, we will just take some examples and see how to perform. Okay. 2's complement for subtraction. So how can you perform this? Say for example, I have the numbers 1101, okay, 0010. I have to subtract 0010 from 1110. If I do the normal subtraction, 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1. So I got 1100 as the answer. So in your this one, when you are doing using 2's complement, take this subtrahend, convert this to 2's complement. First I have converted to 1's complement, then add 1, you will get 2's complement. This is 2's complement of 0010. Okay. Now to this 2's complement, you have to add this number 1101110. So mind you, here you have to add. So this is 0 0 1. 1 plus 1 is 1 0. So 0 and carry 1. 1 plus 1 plus 1 is 1 and carry 1. 1 plus 1 plus 1 is 1 and carry 1. So in while performing the subtraction, uh, you have to neglect the carry when you get. Whenever you are subtracting a smaller number from a larger number, you will get a carry, and that carry should be neglected. So your answer is 1100, which was absolutely right. Now this method is very useful when you have when you have when you have got to subtract a larger number from a smaller number. Okay, that is very difficult for you to do in your normal subtraction. So we will see some examples with that. Okay. Okay, so I'll take some examples to show about that. I'll pick a new slide. Say for example, I want to subtract 15 from 4. I want to subtract 15 from 4. So if I have to represent, 15 is 15 is 1111. I have to subtract 1111 from 4. How do you represent 4? 4 is 100, but I have to make it to 4 bits because 15 is 4 bits. I want to subtract 111 from 4. So obviously 15 is a greater number and 4 is a smaller number. So it is very difficult for us to do using the normal subtraction. So now I will convert this number 15 to 2's complement. First to 1's complement, I'll get all zeros. Then add 1 to the rightmost bit. So I'll get 0001. Now I will add this 0001. This is 2's complement of 15. So now I will add with this number 0100. So what I'll get, you have to add 1010. I got 0101. Okay. So what is this actually? I should have got, see, 15, I'm sorry, 4 minus 15 should be minus 11. Correct? But here it is showing 0101. We don't know whether it is right. Actually, this value is 1011. It is plus 11 here. Means this is minus 11, where our answer is absolutely right. It is showing in 2's complement form, the negative number. No? It is showing in 2's complement form. So, because it is negative, it will show in the 2's complement form. To verify your answer, whether it is right, you can just convert to 2's complement again. So, that will result in your positive number, and obviously this will be your negative number. So, this is how you convert. If you want, I can take one more example and show. Say, for example, I want to convert, I want to subtract 10. I want to subtract 32 from 25. So 32, how do I represent? 1 0 0 0 0 0. This will be 32. 2 per 0, 2 per 1, 2 per 2, 2 per 3, 2 per 4, 2 per 0, 2 per 1, 2 per 2, 2 per 3, 2 per 4, 2 per 5. 32. 32 from 25. So how do I represent 25? 25 is 16 plus 8. 16 plus 8 is 24 plus 1. So I want to subtract 32 from 25. So I will take 32. I will convert to 2's complement. To this I should add 1 to convert to 2's complement. This should be 0, 1, 1, 1, 1. So I will convert this 0, 0, 1, 0, 1, 0, 1, 0, 1. So I got, this is my 2's complement of 32. Now to this I should add 0, 1, 1, 0, 0, 1. This is 25, right? 16 plus 9 is 25. So to this I will be adding this value. So you will get 1, 0, 0, 1, 1, 1. So I got some answer 1, 1, 1, 0, 0, 1. Actually my answer will be in negative. So I will convert this to 2's complement and check. So I am getting 7. So 7 is the answer. Actually this answer what I got was minus 7, which was absolutely right. 32. 25 minus 32 is minus 7, which is right. So now next I will talk about addition for multiple values, because this is what you require for your multiplication. So whenever you're adding any number, say for example, I want to add 17 plus 3, it is 20. So you'll convert it into binary and add. If I say 17 plus 3 plus 5 plus 20 equal to what? So you know how to do it very easily in your decimal, but in binary, how do you do? So how do you represent 17? 16 plus 1, correct? So this is 17. 3, how do you represent 3? 1, 1. So if you don't have anything, you can put zeros. 5, how do you represent 5? Like this. How do you represent 20? 16 plus 4 is 20. Now you want to add all these numbers. So when you add, see, 1 plus 1 plus 1 is 3. So in binary, you represent 3 as 1, 1. Okay? 3 as 1, 1. So put the rightmost bit here, leftmost bit you carry. You got 1, 1. 1, 1 is 0 and a carry of 1. So 1 plus 1 plus 1 is 3. Again, put 1, carry 1. So you get 1. Again, 1 plus 1 is 0 and a carry of 1, and you will write it here. So you got 1, 0, 1, 0, 1, 1, 0, 1, something like this. Okay, this is how you perform the addition. But you will have even more complex values or multiple summands. So how do you represent them? 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, something like this. You think you're supposed to perform the addition. How do you perform the addition? 0 plus 1 plus 0 plus 0 is 1. Then I got 1, 1, 1, 1. So you got 4, 1. That is 4 is the value. How do you represent 4? 1, 0, 0. So the rightmost bit you write here. The leftmost bits, that is 1, 0, you have to carry it. So when you carry this 1, 0, this is 1, 0 is 2. 2 plus 1 is 3, 4, 5. So 5, how do you represent 5? 1, 0, 1. So rightmost bit I'll put here. Again 1, 0 I have to carry. 1, 0 is 2. 3, 4, 5, 6 I got. 6 is 1, 1, 0. So I'll put a 0 here. Carry 1, 1 here. 1, 1 is 3. 3 plus 1 is 4, 5, 6. So 6 means I should put 0 and carry of 1, 1. So I will write it to the left. Now you just see what are the numbers I have taken. I don't even know what are the numbers. This is 14. 14 plus 16 is 30, I think. 30. This is 15. 30 plus 15. This is 10. 10 plus 16 is 26. Then 1, 1, 1, 1, 0. This is again 30. So you sum up all this, you get 11 plus 5 plus 5, 10. So you get 101 as the answer. I don't know whether we have got the answer right. Is it correct? 30 plus 30 is 60. 60, 86, 86, 91, 101. So whether our addition is right, wrong, don't know. So if you just see, this part is 5, 5, this is 0, 8, 16 is 0, 32 plus 64. So 64 plus 32 plus 5. 32 plus 5 is 37. So I'm getting 11, 9, 101. Our answer is absolutely right. So these are some of the important things what you should know for performing your multiplication. Okay. So now we will get into the multiplication part. Here you all can see one such multiplication. Hmm. So whenever I'm trying to perform the multiplication. Okay, multiplication of numbers. How do we do? See, 15 into 10 or 12 I want to do. First I'll multiply this 15 with 2, correct? 5 2s are 10, 2 1s are 2, 3. Then I will multiply this 15 with 1, so 15. Now you will be adding these. These are called as partial products. These are called as partial products, or also we call them as summands. Okay, we also call them as summands. Partial products or summands. So this will be 0, 5 plus 3 is 8, and 1. So I got it as 180. So this is how we perform normally. So when given your binary numbers, how do you perform? Similarly, right? So this is called as your multiplicand. This is called as your multiplier. This is very important. Multiplier, multiplicand. So what you get below is your product. So now 1 into this number I have to do. So I'll get 1011. For the next digit also I have 1. So I have to shift by 1 bit. So I have to write down the multiplicand as it is. Okay. Then the next one is zeros. Because when you multiply anything, it is 0 what you get. So 1. 1 plus 1 is 0 and a 1 carry. So 1 plus 1 is 0 and a 1 carry. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. So you got something like this. So what I had taken, 11 into 3. 11 into 11 into 3 I had taken, correct? So it is 33. So did we get it correctly? You just see. This is 2 per 0, 2 per 1, 2 per 2, 2 per 3, 2 per 4, 2 per 5. 2 per 5 is 32. Plus all these are zeros. 2 per 0 is 1. 1 into 1 is 1. So you got 33. So this answer is right. Okay. Next. Next, what we do is the same logic is used, and circuit is proposed for this. We call it as the sequential multiplier. So what this uses is sequential multiplier. What this makes use is this logic, whatever we saw now. What it uses is, see, you have to multiply. If your multiplier is 1, you get the same multiplicand as your partial product, right? Say for example, I want to multiply something like this. So when you have a 1, you will get the same multiplicand as the answer, correct? Then again I have a 1, I will get the same multiplicand as the answer. Then I have a 0. So what I do, only shifting, and it is 0. So 0 has no value. So you will just get it as 0. When you are performing an addition, you add 0 or not, it does not make any difference. So with this logic, they have designed this sequential multiplier circuit, what I'm going to show next. Okay. Yeah. This is your sequential multiplier, what you can see. So in your sequential multiplier circuit, they follow the same logic. What is that logic? The logic here is they have a control sequencer, okay, which talks about if your here Q is taken as your multiplier. Recall from the previous example, whenever I was multiplying, I first went with the first bit of your multiplier, then next bit, then next bit. So every time I want this multiplier, that is the Q0 bit. Every time whichever bit I have to multiply, that should come to Q0. So every time Q0 bit is checked. If it is 1, they copy the multiplicand. Here you have the multiplicand, okay, stored in this register M, and you have a multiplexer which will select the multiplicand in case your control sequence is 1. If it is 0, it will select 0. You can see here in the circuit a 0 is written here. If this control sequence is 0, it will select 0. If not, it will select this multiplicand. It will give to this adder. The adder, see, we have one register here called as C register, which is 1 bit. We have n bit A register. This is nothing but your accumulator, n bit. Then we have n bit multiplier register, that is we call it as the Q register. So every time what you do is you perform CAQ, right shift CAQ, that is you will be shifting the contents of register C, A and Q towards the right, okay, by 1 bit, because see, every time I want the Q0 bit, that is, say for example, your multiplier is 1011. First time I want 1. After I do this, this bit should go off. So when I do a right shift, the rightmost bit will go. Then the next bit will come to this position. Then the next bit, like that, right? So that is why we do a right shift CAQ. In the division, what I showed you, we had left shift. Okay, here it is right shift. So it will check this. So if it is 0, then no add, only 0. If it is 1, then you have to add. So here multiplexer will select this multiplicand and give it to this adder, and initially this A register is stored with 0, so it will add 0 with the multiplicand if your multiplier is 1. Okay, then that again, that result it will store back. You can see here you have two-way arrow. It will take from here, it will perform the addition, again it will store back. If a carry is there, it will be stored in this carry bit. If carry is 1, it will store 1. If it is 0, it will store 0. And every time this multiplier is your Q register. Every time 1 bit will be moved towards the right. So with one example, we will see how this sequential multiplier works. Okay. So here an example is taken. What is it? 1101 into 1011. That is, your multiplicand is 13 and multiplier is 11. Okay, we'll just see how to perform this operation. Okay. I'm taking a new slide. Okay. So this is your numbers 10, 13, 1101, and multiplier is 1011. Multiplier is your Q register, multiplicand is M. So now we have to follow certain steps for this. I'll just tell you what is it. So now you all recall from this one, you had one C register. Okay, you had one A register. Here we have taken 4 bits, so it can be n bits. I'll take 4 bits. Okay, this is your register A. So register A initially is initialized to 0. Okay, then this carry is also initialized to 0 initially. This is your carry register. Then your Q register is initialized with the multiplier. This is your multiplier. Remember that. Multiplier. Okay. So what is your multiplier? 1011. Okay. This is your Q register. And what is your multiplicand? Multiplicand is 1101. 1101 is your multiplicand. Now, what you are supposed to do, first step, every time you have to check what is your Q0 bit. So this is your Q0, Q1, Q2, Q3. Every time you have to check your Q0 bit. Q0 is 1. If Q0 is 1, then you are supposed to, what is the operation we perform? I'll write down this. So add and shift. Okay. So this is the operation what you are supposed to perform. So now what we will do? We will perform this add and shift. What is your multiplicand? Multiplicand is 1101. So first step is add. So I have to add this 1101. So I'll get 1011 only because I'm adding with 0. Then this bit I will write as it is. Then I will perform shift. Shift is what? Right shift CAQ. When I perform right shift CAQ, see here I have a 0, correct? So when I perform this right shift CAQ, okay, this 0, right shift I'm doing, mind you. So this 0 will come here, this one will come here, this one will come here, this 0, this one will come here, this one will come here, this 0 will come here, this one will come. See, this bit is gone. That is what we want. Now every time our Q0 bit should be moved from the left so that we do a right shift. So this is my first cycle. So what I did, add and right shift CAQ. Why did I do add? Because my Q0 bit was 1. If my Q0 bit is 0, I will do only shift. I will not. Okay. So now this is done. Okay. So nothing is there here. Carry bit will be 0. This was my first cycle. So next, how many steps I have to do? The number of bits in my multiplier is 4. So 4 steps I have to perform. Okay. Then this was my first cycle. In the second cycle, this was my first cycle. I'll just draw a line. So in the second cycle, again, I have to check the Q0 bit. What is my Q0 bit? Q0 bit is 1. Okay. Q0 bit equal to 1. So I should add. When Q0 is 1, I have to add. Add what? Add M to register A. So my register A is 0110. So I'll be adding M. What is M? 1101. So when I add, what will I get? 110. 1 carry is 0 and my carry bit results in 1 here. Okay. Then I have to do a shift operation. Then right shift CAQ. When I do right shift, you all know this bit will come here. This bit will go here. This bit will go here. This bit will go. This one will come here. 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 This bit one will go away. Okay. Right shift CAQ. I have done this. So one cycle is complete. Then again, what I have to do? Next cycle. Again, I have to check for Q0 bit. Here, Q0 is equal to 0. So, no add, only shift, right shift, CAQ. Only shift I have to perform. So if nothing is here, I have to take it as 0. So right shift CAQ. So this 0 will come here, this one, this 0, this one will come here, 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 this 0 will go away. Okay. So now again I have to check my bit. So it is 1. If it is 1, what should I do? Because Q0 is 1, I have to add. Add what? Add the contents of M to with the register contents 1101. I have to add. So when I add, I'll get 10010 and a carry of 1. Then this bit will be same. Okay. So now I have to perform right shift CAQ. Right shift CAQ. When I perform, this 1 will come here, this 0 will come here, this 0 will come here, this 0 will come here, this one 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 will come here. Okay. So what is it? So I have performed how many steps? 1, 2, 3, 4 steps. So at the end of 4th step, because 4 bits in my multiplier, I have to stop here. So this is your product is present in register A and Q together. That is A into Q, you will get your product. So what is in A? If you just check, it is 1000 and in Q 1111. So what is that we had taken? 13 into 11, right? We had taken 13 into 11. So what should you get for 13 into 11? It should be 143, I think, right? So we had 1000 in register A, 1111 in why did we stop at the 4th step? Because 4 bits in my multiplier, so I stopped at 4th step. So what is the answer here? What are you getting? This is 15 plus 16 is not there, 32 is not there, 64 is not there. This is 128. 128 plus 15, you just add and check whether our answer is correct. 13, 143. It is absolutely right. So this sequential multiplier circuit is a very simple one which uses this 0 bar 1. If it is 0, only shift. That is, if your multiplier bit is 0, only shift. If it is 1, add M to register A and do a right shift CAQ. Here also right shift CAQ. Here only right shift CAQ. Here if it is 1, add and then right shift CAQ. So simple logic is used. But what is the drawback of this? What is the drawback of this? This is suitable only for unsigned numbers. That is positive numbers. Unsigned numbers, we cannot use it for signed numbers. That is, when we have negative numbers, we cannot use this technique. So this is ruled out for signed numbers. So we go for Booth's algorithm. Otherwise, for positive numbers or for unsigned numbers, this sequential multiplier is a suitable technique. So hope you all have followed this. Thank you for your patient listening. Hello. Hello, students. Am I audible?
Yes, ma'am.
Any doubts in this? Hello? Anyone has doubts? You can ask. One of you respond.
No, I'm not.
It's clear?
Yes,
Can I
ma'am.
continue for 10 more minutes? Or shall I take one more class for Booth's algorithm and modified Booth's algorithm? If you're, because it's almost 1 hour 20 minutes after I've started, 1 hour 10 minutes. If you want, I will stop here and schedule one more class tomorrow or day after. Shall I stop here? One of you respond. Hello? Shall I continue?
Yes, ma'am.
Shall I continue? No problem?
No problem.
Okay. Okay, I'll at least tell you Booth's algorithms. For modified Booth's algorithm, I'll see if Friday if I can take one class for you all. Okay, offline. Otherwise, I'll do online. Okay. I'll not take much time, just 15 to 20 minutes, because you know all the concepts. Just listen very carefully. I forgot to record this session. Now I'm recording. Good morning, students. Today I'm going to tell you what is the need for Booth's algorithm and with which principle this algorithm works. So this Booth's algorithm can be applied, or it can be used for both signed and unsigned numbers or integers. The previous technique, that is sequential multiplier circuit, was useful only for unsigned numbers. For signed numbers, it was not working. So we move to this Booth's algorithm. This Booth's algorithm follows a principle, that is, whatever we saw just now, um, for negative numbers, sequential multiplier was not working. So here, whatever we saw in the previous one, we got, say for example, I am multiplying numbers like this. So here 3 bits in my multiplier, I will be getting 3 partial products, something like this. I'll be getting 3 partial products. These are called as your partial products. Okay. And one more thing here is, see, whatever we are doing here, we are getting the partial products, we are summing up, and you are getting some answer here. So whenever you have a 1, you have to write down the multiplicand. So this is where your um Booth's algorithm plays a very important role. See, when you have 0 and 0, it is 0 into multiplicand, and when you have 1 1, also it is 0 into m. So this is what he gave us. When you have a stream of ones as your multiplier, so when you recode this bits, okay, you will get it as 0. When you have a stream of continuous ones, then it is 0. If it is 0, you know, just you need not add the multiplicand, you have to just write it as zeros. That is where this Booth's algorithm has its significance. Okay, so this you have to remember, bit I and bit I minus 1. So he does a recoding of bit 0 to 0. When you have two zeros, we do a bit um recoding of the bits for the multiplier bits, not for the multiplicand. You have to remember this. So when you do that, when you have two zeros continuously, you will get 0 into m. That is, it's as good as multiplying with 0. Then 0 into 1. 0 into 1 means, you remember like this, 1 minus 0 is plus 1 only. I'm just telling you a technique for remembering this. Okay, so you'll get a positive 1. So it is plus 1. Then 0 to minus 1. 0 minus 1 means it is minus 1 into m. Then 1 to 1 is 0. So using this table you all have to remember. So using this, you can perform the multiplication. So I'll just write this code for you, so that we can perform it very easily. So I have qi and qi minus 1 bit. So this is 0 0. So what is the version here? 0 into m. So I have 0 1, it is plus 1 into m. I have 1 0, it is minus 1 into m. I have 1 1, it is 0 into m. This is very, very important. So what we have to do is, say for example, I have some numbers. Okay. Now this is my multiplier. This is my multiplicand. Okay. So when I multiply this number, see 0 into this, I will get it as 0. Okay. Then with 1 I am multiplying. So I should write this as it is. With 1 I am multiplying. I should write 1 1 0 1. Again I am multiplying with 1. This is Booth's algorithm. This is Booth's algorithm. So whenever we are using this Booth's algorithm, we have to recode the bits, the multiplier bits, not your multiplicand bits. Okay. So what you are supposed to do is, say for example, I have 13 into minus 6, which I have to multiply. And one more thing what you have to remember is, you have to convert this to binary. So this is plus 13 and multiplier is minus 6. This is plus 13 and minus 6. So plus 13, how do you represent? 13 is 1101. Plus 13 means plus is, the sign will be 0. Then 6. What is 6? 6 is represented as 110, but it is minus 6. So before converting it into minus 6, I will take plus 6 and then convert. But if you just see here, this is 5 bits. So here I have 4 bits. So you should equate to this bit. So I will add a 0 to the left. So this became plus 6. So my multiplier is plus 6 here, but I have to take it as minus 6. So to make it minus 6, I will convert to 2's complement. Converting to 2's complement, I think you all are aware of. Convert to 1's complement. Add 1 to the rightmost bit. So this will be 0, 1, 0, 1, 1. So it is 1, 1, 0, 1, 0. This is minus 6. Okay, this is my multiplier. Okay, then this is my multiplicand. Multiplicand. Okay, so now I will show you how to recode this. So you should recode the multiplier bit 1, 1. Or first we will take one example how this works. Then I will show you uh, how this Booth's algorithm works. So see, I have 1 1 0 1 0. So when I do a normal multiplication, you tell me multiplying with 0 is just zeros. How many bits are there? 5 bits. And mind you, your product, whatever you get, will be twice your multiplicand bits. That is, if you have 5 bits in your multiplicand, your final product will be 10 bit. Your answer or product will be in 10 bits. Okay, that you have to remember. So now here again I have to multiply with 1. So 1 means 1 0 1 1 and a 0 here. Next I have to shift with 2 bits. 2 bits, when I shift, again I have 0. So this will be zeros, 5 zeros, correct? Then I have to shift by 3 bits to 3 bits. When I shift by 3 bits, here it is 1 is the answer. 1 is the multiplier. So it is 1 0 1 1 0. Okay, 1 1 0. Then by 4 bits, shift by 4 bits, then write down, because it is 1 again, so it will be 1 0 1 1 0. Now when I add all this, what will be my answer? You just see, this is 0, this is 1, this is 0, this is 2, this is 3, so this is 2, 0 and a carry of 1. Okay, so 3, again 1, again 0 and a 1. Okay, so this is what I got as the answer. What have I taken? 13 into 6. 13 into 6 should be 6 3s are 18, 78. That is minus 78 I should get. Whether I've got it as minus 78, we will check. Okay, so if you just check this, this is 2. 2 plus, this is 16. 16 plus 2, this is 32, this is 64 plus 128. But actually this is in your 2's complement, because I had taken minus 6. So we'll convert and check whether it is correct. 0 1 0 1 0 1 1 0 1, and to this you add 1. To this you add 1 to get the positive number. So this is 0 1 1 1 0 1 0 1 0, something you got. So what is it? If you see here, this will be 14. 14 plus 32. 14 plus 32 plus 64, 128. If you just check this also, it is not right. Correct? We did not get the correct answer. We should have got it as minus 78. What may be the reason for this? Any guesses? Okay. We did not get the right answer, though we did it correctly. All our procedure was correct. That is, we took the sum, everything, and we did, but we did not get the correct answer. The reason for this was, see here, I told you your product should be in 10 bits. Okay, so here, to make it 10 bits, whatever is the MSB of this partial product, that I have to go on adding. Here MSB is 0, so I'm adding. Here MSB is 0, so I'm adding. So we call this as a sign extension, but the normal multiplication what we are doing will not work for your negative numbers. Okay, so what we do is we go for this Booth's algorithm. In this Booth's algorithm we do the bit pair recoding. Okay, see, you have 11010 as your multiplier bit. This is your -6. This is your -6. So to do this, what we do is we add an imaginary 0. Why imaginary 0 or implied 0 also we say? Why? Because we are making two bits as one pair. So when you are making the actual bits as a pair, then you will run short by one bit. So we add an implied 0. This is called as an implied 0 to the right side. Okay. So now you start pairing it. These two become one pair. Okay. So these two become one pair. 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 Now write down the values. Now I told you na, the table 0 to 0. What was it? 0. Correct? 0 to 0 was 0. Then 0 to 1 transition was -1. Then 1 to 0 was +1. Then 0 to 1 was -1. Then 1 to 1 was 0. So these are your bit pair recoding. Just check one. 0 to 0 is 0. 0 to 1 is -1. 1 to 0 is +1. 0 to 1 is -1. 1 to 1 is 0. So this is where you got this answer. 0, 1, 1, 0. So now, what is this 13 we had now? 13 is 1101. To that I have added 0 into this value 0, -1, +1, -1 and a 0. So I have to multiply this value with this. So 0 into everything is 0. So I'll get 5 bits as 0. Then -1 into this. You should take 2's complement of this. 1, 0. See, this is your m, right? So I'm writing -m. -m equal to 1, 0, 0, 1, 0 plus 1. So you'll get 1, 0, 0, 1, 1 for this. See, 1, 0, 0, 1, 0 plus 1. So you'll get -m as 1, 0, 0, 1, 1. So when you say -1, when you have to multiply this multiplicand with -1, it is as good as -m. So this is your -m value. So I'll write down this value here. Okay, I'm writing this value here. Then next one, it is +1. If it is multiplication by 1, +1, then you just write down this multiplicand as it is. So your multiplicand is 1, 0, 1, 1 and a 0. Then you have to shift by 3 bits. Then it is -1. -1 means again -m you should write down here. So 1, 1, 0, 0, 1. Okay, that is -1. Then it is 0. So add zeros. How many zeros? 5 zeros, because 5 bits in the multiplicand. Now if you just add this, you will get a wrong answer. So what we have to do is we have to do something called as sign extension. What is this sign extension? I told na, if see here, what you have to do is your product should be equal to 10 bits. Here, see, it is equal to 9 bits, 4 here and 4. So I should add 1, 0 to the left, because here the MSB is 0. Here I should add 2 ones because MSB is 1. Here I should add 2 zeros, because 3 zeros, because my MSB is 0. I'll add 0. This is called as sign extension. what is the sign of your partial product. Okay, how do you see the sign? Your MSB bit. Okay, here I'll be adding 5 zeros. Where is my cursor? Here I'll add 5 zeros. Now you sum up all these. What will you get? You see, this is 0, this is 1, this is 1 plus 1 is 0, and a carry of 1, 1 plus 1 is 0, and a carry of 1, 1 plus 1 plus 1 is 3, 1 and carry 1, 1 plus 1 plus 1 is 3, 1 and carry 1, 1 plus 1 is 2, so 0, carry 1, 1 plus 1 plus 1 is 3, so add 1 here and carry 1 here, 1 plus 1 plus 1 is, add 1 here, carry 1, so 1 plus 1 plus 1 is 1 and carry 1 here. So actually this answer will be in negative. Okay, so what we will do, we will convert this to 2's complement to check whether our answer is correct. Okay, so when I convert this to 2's complement, you get 0 0 0 0, then 1 0 0 1 1 0 1, and to this add 1. So when I add 1, 1 plus 1 is 0, carry 1 1 1 1 0 0 1. Anyhow all these are zeros. Now check whether you will get this answer correctly. So this part is 14, this is 64, 64 plus 14 is 78, so this is minus 78, which is absolutely right. So this is about your Booth's algorithm. So it is very useful when you have multiple ones, because it will recode to 0. Hello.